One thing that I did say in the video clips that I would do is to show you the Speiser Driveline angle calculator. What this does is to give you a way of working out whether your operating angles, whether they're within the tolerance that Speiser recommend. What are those tolerances? Let's just have a quick look. If you go onto the little information tab here, it opens up some very interesting notes. This basic rules section is quite interesting. Rule 1, universal joint operating angles at each end should always be at least 1/2 degree. Universal joint operating angles on each end should always be equal within 1 degree of each other. What this means is that you should always have a little bit of an angle on your prop shaft as a minimum. Of course, it can be more than 1/2 degree, but it shouldn't be less than 1/2 degree. Your prop shaft shouldn't be completely straight. I'm not entirely sure why that's a problem, but evidently it is. So it has to be very slightly off straight. And relating to rule 2, the input and output flanges of the prop shaft should be within 1 degree of parallel. Completely parallel is fine, and you can go up to 1 degree out of parallel to each other, but not more than that. If you go further than that, you introduce driveline unequal operating speeds, which translates to vibration. And this relates to the other video clip that you'll see from the Speiser Training Academy. The next thing, rule 3, that Speiser recommend that for vibration-free performance, the UJ angle shouldn't be larger than 3 degrees. So they're saying basically it should be between 1/2 degree and 3 degrees for the UJ operating angles. If they say that if they are, make sure they don't exceed these recommended angles. And it's related, unsurprisingly, to the speed of the drive shaft. Now, I worked out on the Landy that at 60 miles an hour, the drive shaft RPM I worked out is going to be about 3,100. And that translates across to a maximum permissible operating angle of, well, a little bit of an estimate just off the top of my head, let's say 5.5 degrees of maximum angle. Now, in actual fact, you will see in the later video clips that the angle that I'm forced to use on the Landy with the Salisbury axle is actually greater than that, probably nearer 8 degrees, 8.5. However, looking at this realistically, it looked to me as if the original prop shaft with the original axle was probably more than 5.5 degrees of angulation in standard use. So I'm not convinced that this is going to be an important factor. I think the main thing is to ensure that the input and output flanges are parallel. So that's the thing I'm going to really concentrate on. If we carry on now to have a look at the actual angle calculator, all you have to do is you use an inclinometer to work out what the angle is of your input shaft, which they call the driving member, then the angle of incline of the actual prop shaft itself, and then the angle of the driven member, the prop shaft output flange, effectively. Stick these angles in, indicate whether it's an upward or a downward slope, and in the case of the Land Rover, everything is on a downward slope. The gearbox is slightly angled down, the prop then goes further down, and then effectively the pinion of the differential is in a downward direction, so that is also regarded as downhill. So you put those angles in and then it calculates what you end up with. So let's say, for example, that we've got an angle on the input flange of, let's say, 3 degrees. Then we've got an angle on the prop shaft of 15 degrees. and an angle on the driven member, the output shaft, of 4 degrees. Calculate results, and what it works out as that we've got operating angles of 12 and 11 degrees on the universal joint. So according to Speiser's basic rules calculator, you should have problems unless the prop shaft is only designed to rotate very slowly, but this is just an example anyway. But you can see how this works. It's not particularly complicated. You can, if you have a multiple prop shaft system, you can adjust this to give you the angles for up to 4 prop shafts in a system. Now this calculator might be more useful for that because obviously it's a little more complicated, but for a simple Land Rover system with 1 prop shaft, this is all pretty straightforward. So primary thing, make sure the input and output flanges are parallel or within 1 degree of parallel, and then we'll just have to see what the angle of the prop shaft is subsequently. Let's have a look at this clip from the Speiser garage, which covers driveline vibrations and non-uniform velocity. It's quite a good illustration of what this all means. I've actually taken a few sections out of this overall clip to make it a little bit shorter.
Non-uniform velocity is a difference in rotational speed in the input source, like a transmission, the drive shaft, and the axle. The difference in velocity or rotational speed can lead to vibrations in the drive shaft, which can cause significant damage to the drivetrain. Non-uniform velocity occurs for 2 reasons: when the angles between the yoke at the transmission and the yoke at the axle are not in proper alignment, or when the drive shaft is not phased correctly. The phasing of the drive shaft is related to the position of the yoke ears on either end of the shaft. When we have no angle in a drive shaft, the speed should be constant. That's exactly what's happening with no angle. Everything travels at a constant speed. When we put unequal angles in the drive shaft, we cause the rotational speed to change. We can see and hear the effects this has on the drive shaft. This inconsistent rotational speed is then transferred through the drive shaft to the axle, causing a vibration. What we want is the front and rear angles to cancel each other out. When the rear angle is equal to or within 1 degree of the front angle, the rotational speed realigns and eliminates the vibration in the system. As mentioned earlier, the other factor that can cause non-uniform velocity is improper phasing or alignment of the front and rear yoke ears. It is vital that you mark these positions prior to disassembly to ensure you can match the positions during reassembly.
So you can see how important it is that the input and output flanges are within 1 degree of being parallel to each other. So that's what I'm going to look at in the next part of the video. I'll trial fit the Salisbury, and I'll try to ensure that the spring saddles get welded in place to ensure those input and output flanges are almost parallel.